This is example problem number 2, still for lab number 1. And in this case, I want to give you a visualization of the problem before we proceed with it. What I'm showing here in this physical model is I got this little Lego person right here, of course. And it's quite possible that she's in a quarry. These are walls of a quarry, okay? And she's noticing this green layer. That could be, since it's green, I'll suggest it's a bentonite bed. It stands out as green. So she's noticed this bentonite bed. And she recognizes that these are two apparent dips. These are not the true dip of that layer. Instead, they're two apparent dips. And so, since she's a structural geologist and she's concerned about what the true strike and dip of this bed is, she proceeds. She takes some measurements. And this surface, right here, this one, she notes a trend, if you will, of 048 degrees. It's off to the northeast, right? And by the way, north for all of this is shown here, right? So north is that way. Okay. So that has a trend of 048 degrees. This other wall of the quarry, right? I'll turn my pencil around to point in the right direction. That has a trend down this way of 175 degrees. Almost due south, not quite, almost due south. In fact, just 5 degrees east of due south. She further notes that in this wall, the one that has the trend of 175, that the apparent dip, this angle right here between the horizontal surface and this green bed, that apparent dip is 16 degrees. She notices also, she takes notes, that this apparent dip is 22 degrees, a little larger of an angle. Again, that's the apparent dip between the horizontal surface and the green bed. Now, while she's there, while she's in the field, she's envisioning what this surface looked like. And she's doing that, so I'm going to kind of put it back in place. All right, there it is. So that manila-colored surface right here, that is actually the surface that explains those two apparent dips. And its continuation above the surface up here is also shown. All right, so in reality, the true dip is plainly, it's hard to show, but the true dip is plainly over here. And it's going to be the angle perhaps between my pencil, the way it's held now, and the surface itself. That'll be the true dip. And the true strike will be this direction. And it kind of looks like it's going to be a little bit east of north. That's the visualization process. Oh, while we're here, let's also kind of deal with this. I am going to move my Lego person and put her up there. So she is now facing in the correct direction to express the orientation of this plane by the right arm rule. And so her expression of this plane in the end will be something that's a little bit east of north. Not quite sure what it'll be yet. And of course the dip then will be off to the southeast, right? As her right arm is pointing to the southeast. It's mostly east. It's east-southeast. And this, by the way, is the solution by an orthographic projection, or it's part of it. I'll show this at the end of the example problem. The problem is schematically illustrated here in the block diagram. As stated, it says that two apparent dips are measured for a planar geologic surface. Those two apparent dips are expressed here. The first one is 16,175. The syntax of that expression is the same as the plunge and trend of a line, which we haven't actually talked about yet. But realize that 16 degrees is the apparent dip, and 175 is the direction of that apparent dip. Notice it's 3 digits. That implies that that is an azimuth. And the fact that this is 2 digits implies that that is a vertical angle with a range of 0 to 90 degrees, in this case 16 degrees. So that apparent dip could alternatively be expressed in quadrants here for the direction as 16 south 5 east. The other apparent dip, the apparent dip angle is 22 degrees, and the direction is 048 degrees. And notice the leading 0. That again is to make sure that it's clear that that is an expression of azimuth in 3 digits. That could also be expressed as 22 north 48 east. And this explains that these are expressions of apparent dip and the direction of apparent dip. The question then is, what is the true strike and dip of the surface? So, again, I'm giving this a little thought, okay, as to how this problem is going to sit on this piece of paper. And I know there's going to be a construction up in this direction, right, along 048. That's going to take it up here. And there's going to be a construction to the south. So I'm thinking an origin right in here would be a good move. To accommodate that, I am going to put a north line. And I'm now using a centimeter scale instead of a piece of paper. But I think a north line placed at about 10.5 centimeters from this edge of the piece of paper would probably work pretty well. And that will be that line right there. For all subsequent constructions, we'll assume that is north. Again, understanding that some of this is going to go off in this direction and some of it's going to come off in this direction. I think an origin right in, I think about here would work well. And to relate that, that point right there is going to be that point in the block diagram. So let's go ahead and do that like we did before. That's O. Having settled on this as my north reference and this as the point of origin, let's go ahead and put these two directions of apparent dip on this, a map, right? At this point, this is a map. So one of those is this one, 175, which is just 5 degrees east of south, right? It's indicated right here, south 5 east. All right, so all we need to do from that point of origin is to lay out a line that is in that compass direction, 5 degrees east of due south. That will be that one. So that line is in the compass direction 175 degrees. Let's do the same thing for the other one, which is 048 degrees, or north 48 east. So in this case, there we are, north 48, 45, 46, 7, 8. It's right there. North 48 east, and that is that line. And that is 048 degrees. Realize that these two lines are also fold lines, so perhaps it would be wise to go ahead and label those. And the next thing we need to do is to put in our apparent dips. And we might as well start here. So I kind of like that, that practice of, let's just put a tree here. Right? That's the surface. And our apparent dip of 16 degrees in this direction, right? 16 degrees along 175 can be put in right there. And this angle, then, is the apparent dip of 16 degrees. And we should do the same thing under this fold line. But to permit these fold lines to fold downward, some things are going to become upside down. But I'm going to put that under this fold line in this direction, whereas this is a tree on the surface. And in this case, we have an angle of 22 degrees to add. So the apparent dip of 22 degrees, 22 degrees, right there. So here, this angle is that apparent dip of 22 degrees. Okay, we're getting there. We've got this direction of apparent dip, and we have this direction of apparent dip, right? Drawn from an origin, O. What we need to establish next is this depth D, which will be common in this construction and in this construction. We have to be careful here, because look, if I choose a depth from this construction out here, it'll be too large to fit into this construction. So we have to be careful. I'm going to suggest then that we start here, where the depth is going to be shorter. And let's go ahead and do that. So what we're saying with this, for instance, this could be, so here is our female Lego lady. Her name is Barbara. So there's Barbara. She walks out on the quarry wall, and she comes out to this point, and she notices that it's a depth D down to this, right? Down to here. Of course, she's not actually doing this. This is just to visualize the problem. I'm going to suggest we establish the depth D, perhaps at this point, which, by the way, is now, we just established E in this scheme, E. All right? And what we'll do is we will come down. That depth, D, which is very deliberately drawn perpendicular to this horizontal surface, the fold line. The next thing we have to do is transfer that depth D over to here. All right? So let's do that. And I'll take that depth D, transfer it right there, and I need to find where that depth D matches the gap between these two lines. I suspect that that is right there. So I am just going to draw that line now. There's that. And that should be, again, the depth D. And it is. So that is also D. Okay? What that means then, let's go back to this orientation. What it means then is that this point, and by the way, this now is point C. I'm going to do it like this. That's point C in that construction, and I believe that's point D in that. So that's C and D. And then this is E and F. Here and here. Okay, so at this point C on the Earth's surface, it is a depth D down to the dipping plane again. At this point E on the Earth's surface, it is also a depth D down to the dipping plane again. What that means is that points D and F are at the same elevation because these were on the same horizontal surface. what that also means is that these 2 points, D and F, a line connecting those 2 points is the strike line, because strike is defined as a horizontal line in a dipping surface. All right, so in map view, looking down on the top of this surface, that strike line at depth projects upward onto the Earth's surface at points C and E, because C and E lie directly above those 2 points. So this line, I'm going to maybe draw it dashed. This is in fact, I can go ahead and label it that way. Well, I'll put it right here. So that is a strike line at depth D. Keeping in mind, if that's the strike line, right, looks, I don't know, maybe something like north 20 east or something like that, right, that the dip can only be shown in a direction that's perpendicular to the strike. Okay, so that seems to suggest that I need to draw the dip direction. We now know the orientation of the dip direction, and I'm going to draw it passing through this origin. That now is the dip direction. In fact, I can add that. And a construction under that line will show the true value of dip. And that could also be considered a fold line. Okay, and again, here's my tree. What we know is that, if you recall, what's true of this point right here, which in this illustration is point A. That is point A, right there. What we know is that under point A, we go down to depth D, we are again on the dipping surface at that same depth. So let's do that. Let's come vertically from this fold line straight down a depth D to establish where the dipping plane will be in this construction. I'm going to confirm that that depth D is still preserved in that length. And so here I am just going to come down that depth D. So now this is D, and this angle will be, in fact, the true dip. And I can simply measure it. That angle is 30, 31, 35, 36, 37, 38 degrees. Let's do that. This angle, dip, equals 38 degrees. That wasn't so bad. Having determined the dip of the plane, 38 degrees, the only thing left is to determine the strike. And actually, we already know it. All I would need to do is to measure the compass direction of this line right here, since that's the strike at depth D. Since it's the strike at depth D, and strike is defined as a horizontal line in a dipping surface, and since this is a planar surface, that'll also be the strike at the surface of the Earth. And my habit is to do just that. So what I really want to do now is to establish this distance, the horizontal leg of this triangle. All right. And I want to put a parallel line, parallel to that strike line at depth. I want to put that same strike line at the Earth's surface. And I might just do that in 3 places here. That strike line then is right here. I can then use that north reference. So that is, in fact, the strike at surface. And that can simply be measured. And it could be measured right here. And that strike is right there. That's 10, 15, I'll even call it 16.5 degrees. Well, let's just leave it at 0.16 degrees. Close enough. So there you have it. The strike equals 0.16. The dip equals 38 degrees. And the dip direction, then, is really to the east or southeast. So it's east, or you could say southeast. So, and in fact, that is already correct for the right arm rule, right? If I face 0.16, more or less to the north or to the northeast, my right arm, in fact, points to the east or southeast. So by right arm rule, this would be expressed 0.1638. And there you have it. The strike and dip determined from 2 apparent dips. So this is that finished construction placed on top of the physical model that I showed you at the very beginning of this video. And if I remove that, you'll see that model underneath, right? There's that. And what I'll do next is I'll take it apart. But I'm going to raise my camera so I can show you all sides of it. But I'll take this apart and show you how these 2 lines, this one and this one, are employed as fold lines. Okay, so let me take this apart. I'm trying to pull these paper clips off that are holding it together. All right, so here we are again, kind of back in position. And so here we go. So I'm lifting this up, and you'll recognize this as a fold line, and that as the vertical construction under that fold line. Likewise, you recognize under this fold line that there's this vertical construction. Okay, well, that's about the best I can do. I really don't know how else to try to explain